Okay, so it should be recording now. So I want to continue the review of what we've been doing all semester with the applications. And so the application today is to something called Benford's Law of Digit Bias. This is one of the things where I really know what I'm talking about. When I was a very young postdoc, I got an email that began, "Greetings, my name is so-and-so. I'm a senior criminal investigator at the Internal Revenue Service." And it was about 5 minutes before I could, summon up enough courage to read the next line of the email, which was, "I just read with great interest your recent paper in Acta Arithmetica." And first of all, to me it wasn't just that it was an IRS guy reading it, but that I was so young, somebody actually read one of my papers with interest. And so I ended up having a lot of correspondence with the IRS over the years. I will talk more about it when it's not being recorded. I have gone to the IRS headquarters in Boston and given a talk there on the mathematics. Among the many parting gifts they gave me was an Al Capone bobblehead. Can anybody tell me why the IRS is very proud? Yes? They got Al Capone for tax evasion. That's what took him down, not all the other stuff. Got to pay your taxes. So let's keep things in perspective. Okay, so what I want to do today is I want to talk about one of the most important applications of what we've been doing, detecting fraud. Sometimes it's very easy to prove that fraud has happened. A great example is in some American elections, there are precincts that have had more than 100% voter turnout. I'm pretty sure something has happened there. You can't have more than 100% turnout. All right? In a situation like that, it's very easy to know something wrong happened. Somebody stuffed the ballot box. In other cases, it's a lot harder. And it's probably likely that something has gone wrong, that something nefarious has happened. How likely? Is it worth allocating resources to investigate? How much resources? How many of you have read Rosencrantz and Guildenstern Are Dead? Okay, what scene am I thinking of? This is a liberal arts college. You're supposed to be well-read people. The coin flips, where they have over 90 consecutive heads tossed in Rosencrantz and Guildenstern. I won't ruin the book as to is a tail ever tossed, which I know is the key thing that most of us think as we read Rosencrantz and Guildenstern Are Dead. But if you hear 90 consecutive heads, well, this is 1 over 2 to the 90th if it's a fair coin. 2 to the 10th is about 10 cubed. So we're talking about 1 over 10 to the 27. So something is probably going wrong. Either it's not a fair coin, Tom Stoddard is just really bad at mathematics, lots of explanations, but fair coin is low on the list. All right, so the motivating question is for a nice data set, say Fibonacci numbers, I'm a mathematician, for me that's a nice data set, stock prices, street addresses, college, whatever, what percent of the leading digits are 1? So imagine you have no idea of Benford's Law, which hopefully is true for many of you right now. If you just had to guess naively, what would the simplest possible guess for what fraction of the time do I start with a 1? 10%. And then you realize I'm being a moron, it can't be 10%. What are you correct to? 11%, because it's not going to start with a 0, otherwise the number would just be 0. So the natural guess is 10% correct to 11%. Here's a thought experiment, just some random fluctuations. Here's some actual data. Here's the theoretical prediction. Benford's Law, where you have the strong bias of having a 1 about 30% of the time and a 9 only about 4.6% of the time. The next slide is the slide with data. So here's the Fibonacci numbers. Most common iPhone passcodes. Do not ask how I got that data. Twitter users by number of followers. I'm not sure what Twitter is, but I think you all know what that is. Distance of stars from the Earth. Some data sets look closer to the Benford than others. The question is, why do they all seem to have this remarkable bias towards low leading digits? Where is it coming from, and how can we use this? So I want to explain what Benford's Law is. I want to discuss some of the examples and applications. I'll sketch some of the proofs, and if there's time, which I don't think so, I'll describe some open problems. If you are interested in something like this, I will be doing research with students this summer on Benford's Law, and this is another way to provide some sense of what you could do in small. All right. The first is some caveats. And we've talked about how the IRS wants to detect tax fraud. A math test indicating fraud is not proof of fraud. There can be other explanations. So I actually emailed Scott Adams for permission to use the strip, which he has generously provided. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals a round number after 15% tip. You're worse. I will talk more about Williams College and reimbursements off the record, but this is a really big question. Is somebody forging their expense report? A lot of companies say you can hand in anything without a receipt if it totals no more than $25. What do you think the average lunch costs? $24.99, $24.95. Sometimes they might do $23, $38. But around something just below the critical threshold. And that will be very important later in the talk. So here are some examples of places where Benford's law comes into play. Recurrence relations, special functions, iterates of power exponential rational maps, products of random variables, for myself and number theory, L functions, iterates of the 3x plus 1 map, differences in order statistics, a lot of financial data, which is one of the big applications and why the IRS cares so much about this, many hierarchical Bayesian models for those of you who are doing stats. So in terms of applications, here are 3 big ones. Who are my computer scientists? What's the most famous book you should read if you're a computer scientist? 3-volume set, although I think it is now 4 volumes.
Benford's Law.
No.
Code.
No. No.
That is a book and there are 2.
3-volume set, Donald Knuth, Art of Programming. Okay, you should shame for not saying that. Okay. Extremely famous series, very influential. It's not clear which he's more famous for, more influential for, that volume or creating tech. One of the reasons he created tech was he was just pissed at how poorly formatted this book was. And so, being a good computer scientist, rather than just complaining, he actually solved the problem and created tech. So it's many reasons to talk about this. One is analyzing round-off errors in computer science. When you're doing a lot of analysis with numbers, how are the final digits distributed? What's a good way to store numbers? The big one is tax fraud and image fraud and data integrity. Big issue right now in the world is terrorism. Terrorists want to send signals to each other. There are many different ways to do that. One way is to embed images inside pictures. So if you take a picture, it's a bunch of pixels, each picture has a number, say typically 0 to 255. You can change the last digits of the pixel by just a little bit, and you're not going to really change what the image looks like. And what you can do is you can embed a low resolution image and have it masked by a high resolution image. So one question becomes, can you tell if an image has been modified? And so while Benford's law does not apply there, there is an analog of Benford's law that applies in a situation like this, so that you can say with high probability, we think something has happened to this. And you can try to use this to figure out what's going on. All right, so let me talk a little bit about the general theory. So for many data sets, the probability base b of a first digit of d is the log base b of d plus 1 over d. So if we're looking base 10, which we'll do most of the time, about 30% of the time you'll start off with a 1. All right, so here are the Benford probabilities. So some background material. How many of you have taken abstract algebra? In the interest of full disclosure, I have to remind the audience that I have not taken abstract algebra. But one of the things you do in that is you learn about modulus. So everybody has done mod arithmetic, even if you haven't done abstract algebra. If it's 11 o'clock now, what time is it in 3 hours? 2. All right, so we're saying 11 plus 3 is 2. Mod 12. So what mod 12 means is you subtract off as many multiples of 12 as you need so that you get a number between 0 and 12. So that's all we mean by mod. So a equals b mod c if a minus b is an integer times c. We could also look at things mod 1. That's going to be the most important one for us today. So 4.5 mod 1 is the same as 0.5. The significand, if I give you a number, this is basically scientific notation. I can write my number as s sub 10 of x times 10 to the k. K is going to be an integer. It's going to tell me, do I have trailing zeros or am I padding my number with zeros? And then the significand is between 1 and 10. Then two numbers have the same significance if and only if they have the same leading digits. And that makes sense because if you look at what's going on with the two different numbers, well, all the 10 to the k does is it just changes how many zeros I have. If I want to look at the leading digits, I always just move my decimal place over, and then I get a number that's between 1 and 10. So the log base 10 of x is going to be the log base 10 of the significand plus k times the log of 10, or just plus k. So this is where we're using our log laws. I've been sounding like a broken record all semester. Whenever you see a product, take a logarithm. We're going to do that here. This does not mean that even though we're going to use logarithms to analyze things, at the end of the day, if somebody gives you a data set of, say, batting averages, you should be taking the logarithms and looking at the log of batting averages. We still like to talk about the numbers as the actual numbers, but in terms of doing a lot of the mathematical analysis, it is very convenient to do these change of variables. The key observation is the log of x base 10 and the log of x tilde base 10 are the same mod 1 if and only if they have the same leading digits. And the reason is the significance will be the same. All that will differ is the k's. So I'll get a k and a k tilde, but then when I look at things mod 1, since this is an integer, it vanishes. So if you have the same leading digits, your logarithm mod 1 is the same. So this suggests a really good data transformation. So you want to study the log of your data mod 1. So for those of you who've taken real analysis, for those of you who've seen Fourier series, what's really lurking in the background is the function e to the 2 pi I u. So if you haven't seen this before, you might have hopefully heard of Euler's formula. E to the I theta is cosine theta plus I sine theta. Or you might have seen cis theta in high school many years ago. This is extremely important. What's nice about sine and cosine is they're periodic functions. If you increase by 2 pi, you don't change your value. And so what's nice is if I look at u, e to the 2 pi I u, or if I look at e to the 2 pi I u mod 1, these are the same. If I give you a generic function evaluating x and the integer and the decimal part of x, it's not the same thing. The square root of 15.5 is not the same as the square root of 0.5. The integer part matters. And what's difficult is the integer part is going to encode all those locations of the zeros. We want to study just the significand. And what's wonderful about using this in the background is that if we use the sines and the cosines, if we use Fourier analysis, we don't have to worry about those zeros. We don't have to take the mod 1. We can just take the logarithm. And the reason is that u and u mod 1 will differ by an integer, which means we have an integer times 2 pi. So we're doing an integer number of periods. Well, if you add an integer number of periods to sine or cosine, you return to where you start. And this gives us some hope that we can analyze this and get some really great theorems. Okay, so one of the big results is equidistribution. So we'll say a sequence is equidistributed mod 1 if the fraction of the time it lands in an interval AB is just equal to b minus a. So we'll assume AB is some subinterval of 0, 1. If it's 1/3 to 2/3, well then the measure of that interval is 1/3. So 1/3 of the time in the limit I should fall in that interval. Instead of saying equidistributed, what probability distribution does this remind you of? Uniformly distributed. So in some sense it's saying that the sequence becomes uniformly distributed. So if we put delta masses at each of these points, it's going to converge in some sense to the uniform measure. Okay, so here is a theorem that if you choose an irrational number, then n beta is equidistributed mod 1. So if we look at the fractional parts, why do you think we have to choose beta to be irrational? Why can't I take beta to be 1/5? So I want to, yes?
It'll only take on 5 values.
Yeah, it'll only take on 5 values. It'll be 0, 1/5, 2/5, 3/5, 4/5. 5/5 mod 1 is 0. 6/5 mod 1 is 1/5. So it's just going to cycle through those values. So if beta is rational, you're going to just cycle among those values. It'll be an approximation of equidistributed because those values will be equispaced. The remarkable fact is that as long as beta is irrational, this will become equidistributed as you take more and more data points. There are lots of ways to prove this. I like to prove this using Fourier series and number theory. Professor Silva likes to use ergodic theory. Depending on who's lecturing you, you'll get different proofs. Great results should have multiple proofs. Let's do some examples. The log of 2 base 10 is irrational, and the log 1 plus root 5 over 2 base 10 is irrational. Anybody recognize 1 plus root 5 over 2? What's that? The golden ratio. The golden ratio turns out to be the most irrational of all irrational numbers. If anybody's interested, I will talk to you later as to why that is the most irrational. So let's prove the log of 2 base 10 is irrational. Well, if it's not, then it's got to be rational. So if I exponentiate it, I get 2 is 10 to the p over q. I raise both sides to the q, I get 2 to the q is 10 to the p. Well, 10 is 2 times 5, so we get 2 to the q minus p is 5 to the p. The only way this can be true is both sides have to be 1, which means p equals 0 and q equals 0, so the log of 2 base 10 is 0 over 0. Not happening. Okay? If you get bored later today, prove that the log of the golden mean base 10 is irrational. Okay, so what I want to do now is, I could have done a live simulation, but I chose to just use fixed one so I don't have to worry about my computer being able to run. I chose the square root of pi, one of my favorite numbers. And I looked at the first 10 values, and I looked at how often did I get a value between 0 and 1/10, between 1/10 and 2/10. One of the things I like about this is if each interval had exactly one value, it would look like I'm cooking the data. There should be some fluctuation, so it looks like a real number and a real experiment, but not so much that it looks like the data is a bad fit. So does everybody think that this looks like it's equidistributed? What should I do to convince you? More data. Let's look at 100. What do you think? And there's still some fluctuations. I'd be a little suspicious if it was perfect. Are you convinced yet?
More data.
More data. 1,000. Convinced yet?
More data.
All right, I'm going to stop at this point because I don't know if anybody has eyesight good enough to look at the next level beyond this. If you have decent eyesight, you could probably see little bits of dips as you go around. This interval over here looks like it's a little bit less than the interval on both sides.
When this is 1, does that mean? I mean 1,000.
I'm sorry?
I figured.
Okay. So the whole area under the curve should be 1. Each bin has length 1/10. So a big question is, how quickly does the equidistribution set in? At 10,000, it's setting in fairly quickly. Square root of pi is a nice number. So here's the fundamental equivalence. This is the key to an enormous amount of Benford studies. If you have a data set xi, it's Benford base b if and only if its logarithms base b mod 1 are equidistributed. So this becomes a great way to find out if something is Benford. Look at the logarithms mod 1, see if they fall uniformly, see if they're equidistributed, and if so, you have Benford. Why is this the case? Well, let's write x as the significand times 10 to the k. When we take the log and we look at mod 1, we see the k doesn't matter. So now what I'm going to do is, here are the numbers from 1 to 10, my significance, and here are the logarithms. The log of 1 base 10 is 0, the log of 10 base 10 is 1, the log of 2 base 10 is about 0.3. Let's say my numbers fall evenly when I look at the logarithms mod 1. Well, if they fall evenly, what fraction of the time do I land between 0 and 0.3? I'm sorry? 30%. But if you exponentiate, those are all the numbers whose leading digit is 1. And so what happens is, on a log scale, everything is uniformly distributed, but when we exponentiate back, we're going to get a little bit of a bias. If I want to have something with a leading digit of 5, it's a little bit easier to look at it like this. Let's say I want a leading digit of d. So I want to go from d plus 1 to d. So I subtract the logarithms. Well, the difference of the logs is the log of the quotient. And that's where you get the log of d plus 1 over d, or the log of 1 plus 1 over d. As a nice check, if you add up all of these probabilities, you do get 1. And so this is Benford's law. If you can show the logarithms mod 1 are equidistributed, you have Benford. The question is, can you do this? And one of the great techniques for studying problems like this is Fourier series. It's these sines and cosines. And the reason they're so powerful is because you can take the mod or not. It's up to you. It's not going to change the value of cosine 2 pi u. All right, so let's do some examples. 2 to the n is Benford base 10 because the log of 2 base 10 is irrational. So now, if we look at 2 to the n, if we take the logarithm of this, we get n times the log of 2 base 10. The log of 2 base 10 is irrational, so by our theorem, the fractional parts of n log 2 are equidistributed, so when you exponentiate, you get Benford. Let's look at the Fibonacci numbers. We've talked about the Fibonacci numbers many times throughout the semester. We have this fundamental relationship, an plus 1 is an plus an minus 1. We guess an is r to the n. We get a really nice polynomial equation called the characteristic equation. We solve the roots of r equals 1 plus or minus root 5 over 2. It turns out if r solves this, so does 2r or 3r or 4r. You can multiply by any constant. You can add two solutions and it's a solution because it's a nice linear recurrence. And so you get the general solution is C1R1 to the n plus C2R2 to the n. And then you just look at the first two values to figure out what C1 and C2 are, and you get Benet's formula. And again, I always find Benet's formula miraculous. You've got square roots, you've got division, it's always an integer. What can you tell me about the number 1 minus root 5 over 2? It's irrational. What else?
It's negative.
It's negative.
It's the conjugate of the golden mean.
It is the conjugate in some sense of the golden mean, but there's a very specific property about it that really, really matters. When you look at this formula, when you look at Benet's formula, if I could only give you one of the two terms, which term would you want, the first term or the second term? Which is the more important one for n large?
The 1/2.
I'm sorry?
The 1 over 2.
Yeah, the first one?
Yeah.
Why is this more important than this one? I mean, you asked me to choose between my kids, I won't. But between these two terms, absolutely I'll take the first one. Why is the first one so much more important than the second one? It's a lot bigger. What can you tell me about the size of 1 minus root 5 over 2? Approximately how big is root 5? 2 point something. So when we do 1 minus 2 point something, we get negative 1 point something. When we divide by 2, we get a number less than 1. We raise this to the nth power. One of the things you need to become really good at is quickly glancing down and getting order of magnitude estimates. This is negligible for very large values of n. What this tells you is for large values of n, the nth Fibonacci number is approximately this. Well, this is an irrational number. This number is extremely small. So in fact, the nth Fibonacci number is whatever's integer closest to this. So this becomes a really nice way to quickly get your Fibonacci numbers. So if I want to understand what's going on, I have to, of course, worry about this, but this is going to be a very small pollution. If I can just understand this number, I'll be fine. And now if I take the logarithm of this, well, the log of a product is the sum of the logs. The log of 1 over root 5 just shifts things down. So if it was equidistributed, if I now shift things, it's still equidistributed. And now I have n times the log of the golden mean. The log of the golden mean is irrational. On a logarithm scale, this is equidistributed mod 1, so it's Benford. The only difficulty is I have this little factor here. But this factor, it's so hard for this to change the leading digit that you can just go through and do the detailed analysis. It's a really good problem if you want. I'll make this extra credit and show that if this is equidistributed, this little pollution will not change the equidistribution. Most linear recurrence relations turn out to be Benford. So the first one we looked at, you could write, the 2 to the n as an plus 1 is twice an. What about an plus 1 is 2an minus 1? This one's a little bit more interesting. Let's take our first two terms to be 1 and 1. What will the next term be? And the next term? And the next term? So this one would have an extremely strong bias. Let's take our first two terms to be 0, 1. What would the next term be?
Negative 1.
Nope, 0, 1. Next term is 2. Next term.
3.
Next term.
4.
Next term.
5.
You can probably conject it now at this point. So it would be 1, 2, 3, 4, 5. A great Spaceballs password. Okay? Do you think that's Benford? 1, 2, 3, 4, 5, 6, 7, 8. No. The probability of having a first digit of 1 is going to fluctuate depending on where you stop. So the problem with this is if you calculate the characteristic polynomial, you have a double root of 1. And the double root of 1 in terms of the limiting behavior, it's going to cause some issues. Okay, so let's look at 2 to the n a little bit more closely. We know this is Benford. The numbers get very big very quickly. So to have a decent sized data set, I'm going to look at 60 values, but I can only display the first 60. Over here are my 9 digits. Here's the number. Here's the observed probabilities. Here's the Benford probabilities. So imagine you're now working for the IRS and you're trying to decide, is somebody making things up? You believe the digits of 2 to the n should be Benford. This is what you observe. Do you think something nefarious is going on? And if so, where? Yes?
All the numbers are very rational, so it seems like they just use computer programs to simulate something close to Benford.
But we only have 60 data points. So we have a very, we're looking at, so
Oh, we only see.
we have only 6. But I mean, nothing the IRS ever uses will have an irrational number. So good try, but it's not going to be the rationality.
Seems pretty Benford.
Seems pretty Benford. Where are you more suspicious?
The second digit.
Higher digits.
The high digits. Which one in particular?
9.
The 9. I'd say 9 is worse than the 7 because just percentage-wise as to how much you're off by. Now, how many of you have taken statistics? Okay. So for those of you who haven't, if possible, try to correct that next semester or next year. 60 data points. We talk for the central limit theorem, 60 data points is a lot. But we want to talk about how many events do we expect. The number of events we expect with the first digit of 9, if it's only 4.6% probability and we only have 60 data points, that's less than 5 observations. In statistics, they often talk about you want to have at least 5 events per bin. What you might want to do is you might want to combine some of the low digits and maybe look at 7, 8, 9 all together. And if you do something like that, it's not so bad. 83 and 17 is 100. This is 133. This is maybe 100, 140, 150. So it's closer. But I think we all agree that 9 is the worst. There is an explanation for what's going on. So if we go back to Dilbert, sometimes it's not anything nefarious. Sometimes there's a natural explanation going on. All right, so we're my computer scientists again. So you guys are in the doghouse for not getting out of programming. I will give you a chance to get out of the doghouse, okay?
I'm glad we sat separately today.
How many megabytes are in a gigabyte? 1024. Who are my Latin and Greek scholars? If you hear mega and giga, how many megas should be in a giga? 1,000. So is this just because computer scientists do not understand our ancient languages?
No, it's because Latin and Greek scholars don't understand.
I cannot argue that Latin and Greek scholars do not understand modern computers. And by modern computers, I don't mean the stuff in the book I was showing you with punch cards. Why do computer scientists use the notation incorrectly? It's close enough. 2 to the 10 is 1,024, is approximately 10 cubed. Let's imagine 2 to the 10th was exactly 10 cubed. What would happen every time you go down 10 steps in the Fibonacci's? Oh, not in the Fibonacci's, in the 2 to the n. If 2 to the 10 was exactly 10 cubed, what would happen every time you go down 10 steps? You pad by 3 zeros, you pad by 1,000. If you look at what's going on, 1, 1,024, 104, 8576, it's almost padding by 1,000. It's off by about 2.4%. That's not a lot, but eventually it starts to accumulate. If you look at 512, 524, 288, 536, notice no number has changed its first digit. In fact, we have no 7s. It takes a while before we even see a 7. But it will eventually start to happen. So the question is, what's the rate of convergence? The reason the convergence is slow is 2 to the 10 is almost an integral power of 10. And that's going to be extremely important for the IRS. So I did not choose 3 random numbers. I chose 3 of the most important mathematical constants of all time. Can anybody identify any of the constants? Pi, E.
Golden ratio.
Nope, not the golden ratio. Golden ratio is phi.
Oh, pi over.
Nope. Anybody know what gamma is?
E over 2.
Nope. That's more like what a physicist would do. No. It's the Euler-Mascheroni constant. It's about 0.577. If you look at the harmonic series, the summing of 1 over n up to some x and you want to approximate it, gamma comes in something like this. All right. Who is a pi geek or willing to admit to being a pi geek? How many people can give me at least 2 digits of pi?
3.141.
5 digits of pi? 10 digits of pi? 100 digits of pi?
I want to hear you do 10.
Okay.
All right, 10.
3.141592653589799. I passed 10, right?
I think, yeah, easily. Okay, all right. How many people can give me 4 digits of pi squared? Wait, you all stopped at pi? Nobody memorized digits of pi squared? pi cubed. Oh, this is sad. So you guys don't know high powers of pi off the top of your head? Wow. I'll assume nobody knows pi to the 175 then? What do you think pi to the 175 is close to? I'm sorry?
3 to the 100.
Nope. So what we're doing here is we're doing a chi-squared test. The smaller the chi-squared value, the better the fit. And so if your theory is doing a good job 95% of the time, you should have a chi-squared value of 15.5 or less. This is one of the big stats tests. What distribution do you think you use in a chi-squared test? Chi-squared distribution. So one of the reasons why we do all the theory of chi-squared distributions is for chi-squared tests, for these goodness of fit tests. In Sesame Street, one of my niece Justine's favorite skits is one of these things is not like the other, one of these things just doesn't belong. So when you look at the data, which one does not belong? Pi. It starts off horrendous, gets better, a little worse, gets better, gets much, much better. You finally think, okay, pi has settled down, and then pi just jumps up again and becomes very large. It's getting smaller, but it's also getting larger as well, and it's all over the place. The other ones, at least, going down. Now, they're not going down uniformly, they jump up, but they're not getting to these horrible extremes. Why do you think pi, when I'm looking at Benford's law of powers of pi to the n, why do you think pi to the n is further from Benford than e to the n and gamma to the n? What do you think is going on?
Is it because pi squared is close to 10?
Not pi squared. Not pi cubed. I even told you the number. Pi to the 175, right? If you had only been a little bit more geeky when you were younger. So here is a plot. Okay, the red is the chi-squared value. I'm taking the logarithm so it fits on the scale of pi to the n, and the blue is of e. I need to do this because the chi-squared values of pi are just so much larger than those of e, you just wouldn't see the fluctuations in e at all. When you look at the pattern in pi to the n, what do you see? What does this behavior look like?
8 to multiple 175.
Yeah, I mean, if you look at what's going on here, I start at 0, and then I come all the way down, I go all the way down. Where is this point down here, approximately? Yeah, it looks really close to 175, and it looks like it's periodic, where the amplitude is decreasing as I get more and more data points. So I have some kind of underlying periodic behavior with decreasing amplitude of approximately 175. Pi to the 175 is 1.0028 times 10 to the 87. Every time you go through 175 steps, you almost pad by 87 zeros. Much less than 2. In 2, every time we did 10 steps, we were off by 2.4%. Here we're off now by 0.28%. Powers of pi will be Benford, but it'll be a much slower rate of convergence because of how good pi to the 175 is to being an integer power of 10. So for those of you who like algebraic number theory and stuff like this, how well you can approximate numbers by rationals comes into play here. Okay, so why Benford's law? So I want to give you a sense of why Benford's law holds and then go through some applications. So not all data sets satisfy Benford's law. So we talked a little bit about this. Imagine you have a very long street where the houses are labeled from 1 to L. If you stop at the 199th house, you've just gone through a whole swath of houses starting with a 1. And you'll have over half of your data beginning with a 1. If you stop at street with 999 houses, then you've just gone through an incredible stretch of non-1s. And so you'll see that the probability of a first digit of 1 oscillates between about 1/9 and 5/9, depending on how long the street is. And so here's a little plot. So the probability of a first digit of 1 as a function of the street length. Okay. A huge part of this course is how to view data. And we're going to really emphasize this on the last day of class. There's a better way to view this. I should not be plotting it like this. What should I plot? What transform should I look at? Log. Really, if I go from street ending at 100 or 1,000 or 10,000, I want to, in some sense, consider these very similar. So if I now plot the probability as a function of the log of the street length, Look at that now. The behavior is much better in terms of compressing things and seeing what's going on, and seeing that I have a really nice, essentially cyclic behavior. This small pollutions from small values, as you go further and further down, those small values mean very, very little. What if we have many streets of different lengths? We are not a communist society yet. We are allowed to have streets of different lengths. Let's look and see what happens. So I'm choosing now 1,000 streets. Each street is numbered from 1 to 10,000. And so here in the solid blue is the Benford. Here is my histogram. And not surprisingly, you can see that it is not even close to Benford. What I'm doing now is I'm choosing 1,000 streets, and the length of the street is a randomly chosen number from 1 to 10,000. So I have lots of streets of different sizes now. Benford or not Benford? Not Benford, but closer. Now what I'm going to do is I'm going to choose a number randomly from 1 to 10,000, and then choose a number randomly from 1 to that, and use that for my street length. So I'm going to iterate the process. Benford or not Benford? It's much closer. Let's do it one more time. Benford or not Benford? So already at 3 iterations, the fit is extremely good to Benford. Now there's some little fluctuations and little dips here. These could be very interesting to study. The conclusion is the more processes you have, the closer it is to Benford. What does this remind you of? Central limit theorem. So not surprisingly, there is a central limit theorem lurking in the background here. And those ideas can be used to prove why Benford behavior comes out. So hopefully by now you recognize this slide, and we can go through the slides somewhat quickly. I'm trying to alternate between filling in and not filling in, so today will be a fill-in day. P of x is a density if it's non-negative. If it integrates to 1, the probability x takes on a value between a and b is the area under the curve from a to b. This is why we like integrals. The mean is just the integral of x p of x. The variance, how far spread out, x minus mu squared. What's the next point? I'm sorry?
Integrates to 1.
We've already done integrates to 1. I'm sorry? No? Wait. So today it's, I thought it was Gaussian. I got it wrong myself. Today it's independence. Sometimes I put Gaussian. Knowledge of one random variable gives you no knowledge of others. All right, so I put the Gaussian on the next slide. A little bit different today. So the normal, mean mu, variance sigma squared, 1 over 2 pi sigma squared square root, e to the negative x minus mu squared over 2 sigma squared. So the central limit theorem is if you have a bunch of independent, identically distributed random variables, and you can weaken those assumptions with finite higher moments, then the standardized sum converges to being normally distributed with mean 0, variance 1. And we've talked a lot about why we want to standardize. And now we can compare to just one normal distribution. So let's actually look at some sums of independent random variables. So let's take a uniform. We'll talk on minus 1/2 to 1/2, and then we'll later adjust to have mean 0, variance 1. And we'll look at this calculation. So does the uniform look like a Gaussian? Yes or no? Not really. It's not horrible, but a uniform variable is not a Gaussian. What about sums of 2 uniforms appropriately normalized? Well, it's the triangle. If you think about rolling 2 die, if you look at the sums of the 2 die, you have one way of getting 2, you have one way of getting 12, you have 6 ways of getting 7. It's a nice triangle. This is just the continuous analog. Normal or not normal? Getting there, right. That's the right answer. It's not normal, but it's not so bad. Now let's do 4 of them. And the reason you want to do 4 is it's much easier because we can group things. We now have a triangle plus a triangle. Normal or not normal? Not normal, but getting closer. 8 of them. Getting really close now. So with just 8 sums of uniforms, it's already very close to a Gaussian. You can write down the density function exactly. So here's the density function of the sum of 4 uniforms. Mathematica hung up for me when I tried to get it to do in closed form sums of 8. I may not have waited long enough. You do not want to work with something like this. This is an explicit closed form expression. I talk all the time about how I love explicit closed form expressions. I don't love this explicit closed form expression. I would much rather approximate it with a Gaussian and work with a Gaussian, and then just control the error, especially in the limit as things get very large. I don't want to deal with something that's a nightmare like this. Let's look at the normal mod 1. And so I'm going to choose the variance to be 0.01. And if you look at the normal mod 1, well, if the variance is 0.01, is my probability very high that I'm near 0 or very low that I'm near 0? High. You don't expect to be much beyond 0.02. And if you look at this, yes, here's the 0.02, and here's the stuff coming on the other side, the negative values. So if you look at the normal mod 1, if the normal has a very small variance, it's not even close to uniform. And I've drawn the uniform as a solid line over here. Well, now let's let the variance be 0.1. Is the log of the normal mod 1 uniform? No, but it's a lot closer. Let's look at the variance as 0.5. Is this close to uniform? Yeah, you have to look at the scale on the y-axis. And the scale on the y-axis goes from 0.99990 to 1.0001. So the y-axis is having almost no fluctuations at all. So it is extremely close to normal as soon as the variance is already 0.5. I'm sorry, it's extremely close to uniform. Why is this important? So by now you should have a Pavlovian response. If you see a product, you take a logarithm. Okay? If I have done nothing else to you, please leave this class learning that. Let's say we have a bunch of nice random variables, x1, x2, and let's look at their product. So maybe I want to know how much a bar of gold is worth, and I choose the length, the width, the height from some random variables. I maybe choose the value of gold from another random variable, and then the product of all these will be the value of the gold bar. The more products I have, the more likely it is a central limit theorem should kick in. Well, let's let yi be the log of xi, and let's let vn be the log of the product. Well, so vn is the log of the product. The log of a product is the sum of the logarithms. Well, those are just y1 plus yn. What do you know about sums of independent, identically distributed random variables? They converge to being normally distributed. So now we have something that's converging to being normally distributed. The mean could be growing, and the variance is going to be growing. But a normal distribution with growing variance, what do you think that converges to, mod 1? The uniform. So if you want to look at the central limit theorem in other spaces, if you look at the central limit theorem mod 1, it's actually the uniform distribution. And then when you exponentiate back, you get Benford. So this is one reason, this is the fastest explanation I can give as to why Benford kicks in so many different places. You have so many different processes coming in that on the log scale, you have the central limit theorem kicking in with the growing variance. And a growing variance is going to give you uniform mod 1. All right, applications. So a tale of two Steve Millers. You should hopefully be able to identify one of the Steve Millers. Anybody know who the other one is?
IRS fraud.
The IRS fraud guy. So there was a huge scandal where the IRS was found to be deliberately targeting groups because of their political beliefs. And some people in the IRS got into trouble, including the commissioner who was forced to step down. If you're going to target people, you should not do it for political reasons. You should do it for mathematical reasons. So I will talk to you about how you can use mathematics to figure out whom you should target. If you want, you can look at this. This is the tax return of somebody named William J., married to somebody named Hillary. One of my colleagues who got this says, it's amazing what a couple of $100 and the Freedom of Information Act can get you. So I'll let you look at, if you want, tax returns like these and some notes. Here is a great fun example. An audit of a bank revealed a huge spike in numbers with leading digits starting with something blah, much more than would be predicted by Benford's law. Which digit do you think had the spike?
7.
No. 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 5 is close though.
6.
No, not 6. 4. Yes. Starting with 4. So they did further investigations because they noticed they were having a lot more 4s as leading digits than they were expecting. What do you think the second digit was most of the time? 9, 8, and 9. And it turns out most of this was due to one person. Anybody ever lose a credit card? What happens when you lose a credit card?
Call the bank and then
You call the bank and you say, I lost my credit card. And the bank says, that's fine, just pay us for what was charged on your credit card, right? No. What does the bank say? We'll send you a new card. Don't worry about the charges. Now imagine you're the bank and somebody reports a credit card stolen and there's $35.12 in disputed charges from a gas station. Are you going to send an agent to investigate and track down the thief? No. you see that 15 plasma TVs were just purchased from Walmart. What are you going to do? So if you're the bank, how do you make a decision on investigate or not investigate?
$500 or $50.
Well, $50?
$500.
500? 5,000. So the write-off limit is about 5,000. Any Seinfeld fans here? The great episode where Kramer breaks, Jerry's VCR is broken, and so they're going to try to write it off and claim that the post office destroyed the VCR in shipping. And Kramer's trying to explain to Jerry about the whole process of just writing something off. So the credit card company will just write it off if it's under $5,000. It's just not worth their time. Small potatoes. More than $5,000, they'll investigate. So what was happening is one person was having his friends or her friends, I forget which, take out credit cards, run up debts of almost $5,000, and then call up and wait till they got him. Oh, your card, oh, I'm so sorry to hear your card was stolen. Don't worry, you're not liable for the charges. And they could write it off without triggering an internal audit because it was below the critical threshold. So if you're the bank, what kind of control should you put in place so that this does not happen?
You see a lot of 4 9s.
All right, well then you just do it at 4,600.
You see a lot of 4s.
Vary what the limit is. If you have a hard cutoff, this is one of the reasons why grandma in a cane needs to be searched by security. Because if the terrorists know that there is somebody who can always get through, well, I'll disguise myself as a grandma with a cane. Now, when you're trying to decide how often do you want to pull over grandma for additional security, probably not as much as some other characters. And that's about as far as I can go without getting into trouble. Okay? You want to figure out how do you allocate finite resources. Anything over $5,000 you investigate. Then what would you say is your next decision? Would be a good rule of thumb, maybe.
Anything over 4 that's low is investigate half the time.
Yeah, maybe half the time, 80%, some kind of rule, so that anything between $4,000 and $5,000, you investigate a good fraction. You don't have a sharp cutoff. And then eventually you get to the point where $50, if you want to steal $50, steal $50. It's just not worth our time. And so having a sharp cutoff is very bad. For those of you who are going off into the real world, control theory, things like this is a really good thing to think about so that you don't get stuck into a bad thing. Here's some streamflow data that I analyzed and wrote a paper in geology with an accountant. We have over 100 years of data, almost 500,000 data points. You see a beautiful fit to Benford's law. In fact, we have so many data points that the standard chi-squared tests tell us it's not Benford because we can detect very, very small fluctuations. Election fraud around in 2009. There's a lot of stuff as to was there fraud in that election. One of the good tests you can look at is look at the last 2 digits. The last 2 digits should be uniformly distributed. So you should have the last 2 digits being the same, what fraction of the time? What fraction of the time should the last 2 digits be equal, approximately?
1%.
Not 1%. 10%. You can choose the second to last digit arbitrary, and then the last digit has to be, so about 10% of the time you should have the last 2 digits being the same. And so you can look at patterns about how often do you have double digits ending. So there are lots of different tests you can do for stuff like this. So we're not going to get into other stuff. There's some stuff, if you want, on the Riemann zeta function. There's some stuff on 3x plus 1. There's some stuff on stick decomposition. Just some very fast conclusions. We want to develop more sophisticated tests for fraud. I'm not going to go into all the stuff over here, but how do you determine something bad has happened? Just because it looks unlikely doesn't mean it is. You want to figure out when should you pull the trigger and do the audit. The audit is expensive. The probability can be used for that. I have sent a new test for tax fraud to the Internal Revenue Service. I've been waiting 5 years for them to get back to me on using this. But if anybody's interested, I'm happy to talk to you about that off the record. All right. One more class to hope, no tech failures.